Hello there. So, this is a bit of an impromptu video. I'm going to talk about why I'm interested in math. Whoa, don't leave. Don't leave yet. Don't leave yet. Okay. Well, actually, if you really hate math, well, here's the thing. I will be talking about how a lot of these things are connected. Math, programming, game development, and there's one other thing. Physics, yes. Those four things, math, programming, game development, and physics, are all really super interconnected. And so I will be talking about them quite a lot here on this channel. It's not going to be only game development. So some people wonder, oh, look at you, you're making a video about math. Ew, gross. Okay, if you want to be a really good game developer, look, you can, if you hate math, I guess you could focus on 3D modeling. Okay, so if you're a builder in Roblox, okay, eventually, you know, Roblox is not going to last forever. Not only that, your passion may wane. You might not be passionate about Roblox forever. So you need to kind of expand to other things at some point. Oh, look, there's naughty business over here. What is this? Move that out of the way. But yes, we all need to grow, and also Roblox is not going to last forever. I mean, technically, like, the software doesn't disappear, but maybe, 20 years from now, maybe there won't be many people playing it. There'll be better things out there, perhaps. So we need to grow, and if you really hate math, okay, maybe you can focus on the building side of it. And how do you grow then? Well, you might want to grow by eventually doing things with Blender. Blender is tough. It's really tough. 3D modeling is not easy. And to be honest, it can involve math, but it doesn't have to. I think there are probably 3D modelers out there who really dislike heavy math. Okay. However, if you really want to be a programmer, now there too, you can become a programmer who avoids heavy math, who dislikes math. However, not really a game developer, I have to say. You might be able to. I mean, if you practice scripting for Roblox and you enjoy it, yeah. And you can kind of avoid some math. You do need to kind of learn a bit about vectors. Well, it's really just positioning things. And with rotations, there's some complicated stuff going on there. But let's see. You can kind of avoid it. You can kind of be like, well, I just want this rotation to happen, right? And avoid like the really gory math details. Now, if you want to move the camera around in a fancy way, there might be some packages and stuff, or plugins and stuff, that can boil that down for you and make it approachable. So you could possibly be a game developer, and, well, you could possibly be a game developer who dislikes math. It's possible. However, the fact, I'm not going to sugarcoat it for you. If you want to be a great game developer or a great programmer, you can't be afraid of math. So, do you need to be the next Einstein? No. But I would encourage you to embrace math and, of course, obviously embrace programming. So, these videos about math, some of them will be, like this video, even if you dislike math, you may be able to gain some things from here. Just the overall picture. It's valuable to know how these things are connected. Mathematics, programming, game development, physics, these are all intertwined in a complicated web of relations. And that sort of top-down view is something that I can help communicate, because I've really dug deeply into the rabbit holes in these places. I am 36 years old right now, and I started getting really interested in physics like 10 years ago. And also programming. I've done a ton of programming for over the last 10 years. And a bunch of game development stuff. Okay. And mathematics, I didn't do too much college. I didn't take any college level math courses, except what I did in high school. Actually, my high school stuff was sort of college level, a lot of it. But and then after high school, I tutored math for a few years, including tutoring calculus a bit and all that. So I was a pretty gifted math student. But anyway, enough about me. So yeah, let's get into it. What did I even want to talk about? I wanted to kind of share today why I'm interested in... Actually, my greatest interest really is physics. I find that to be the most interesting thing. And I think for some, it's of course boring, and maybe they have a weird image of physics in their mind. Funny thing is, I failed at the first recording of this. I recorded 8 minutes, and then I ran into a problem and stopped. And this video is turning out to be going down a different road. But it's all going to end up being roughly the same stuff, I want to say. Is this working? Yes, it is. Okay, so I want to speak to people who dislike physics, or like they think physics is ick. They want to avoid it as much as possible. And I want to say that physics is basically the mother of all science and sort of the foundation of everything. So for some people that actually is obvious, but for a lot of people it's not. So physics is kind of this base down here, this foundation. Did I make it so? Ooh, I did. Yay, I made it so I can scroll down. Now, you could say that as a foundation of physics, there's mathematics. So we might... Should I do this the arrow the other way? Let's do the arrow the other way, actually. I'm not sure... Let's just make like a pyramid shape. Supporting physics is math. Basically all... Now, I mean, you can have an intuition of physics that is sort of based on pictures and feelings, but proper physics is all mathematics. Okay. So, but what about our world up here of daily experiences? Well, take, for example, let's take something very high level, like, let's say the economy, or... economy or politics, or let me move this out of the way so I can look at it separately. Economics, the economy, politics, how about like culture and sociology? By the way, this stuff, I'm gonna get a Wacom soon. Anyway, so it'll be faster. Culture, what's the other one? Sociology, like how society is structured. Technically, economics is the study of these things. Sociology is the study of society, I guess. But yeah, you have all this kind of... Is culture science? No, not really, but economics is, in my view, a kind of science. People have criticized it as not being a kind of science, but there are experiments in economics. There's sort of behavioral studies. There's game theory stuff, where you can do experiments. And so psychology really ties into here. And so I actually want to say that the foundation of this stuff is basically human behavior. And so human behavior, I'd like to be able to write this stuff faster, but sorry, I'm using a mouse. Human behavior and psychology. Okay, how the brain works, this kind of stuff. Okay. And what is this based on? Well, this is based on biology. I'll put it here. Biology and what's the word? Biological chemistry, is that the one? Biological chemistry? I think there's a better term. Oh, biochem, biological chemistry. Determines how the brain works, right? So how the brain works is in here, in psychology. Now, if we were simpler organisms like ants, the ants kind of do have a societal structure, right? And they have a brain, so they have a way of thinking, and the chemistry of their brain determines how that brain works, and so on. And what determines how biology works and all that is mainly chemistry. Now, you can also throw in gravity, but yeah, gravity. We don't normally think of gravity as part of chemistry, so I'm going to put it kind of on its own. But mainly we think of chemistry. Okay, so chemistry. And so what describes chemistry and gravity is physics. And some people don't know this, but smart, developed, educated people all should know that chemistry is basically determined by physics. There's something called quantum chemistry. So, gosh, I wish I could write faster. QChem. Quantum chemistry. I'll just erase that. But yeah, physics is this foundation that explains all of chemistry. Okay, so if people go really deep into chemistry, like they're going to PhD level stuff, they study quantum mechanics and quantum chemistry, which is just quantum mechanics, but it's with a focus on chemistry. So if there were anything here in chemistry or the study of physical phenomena in general, if there were anything here that conflicts with physics, you could say, well, that would be a problem. Or you could say that it would create an open question related to physics. And there are such things, like there's, for example, dark matter and dark energy. Those are examples where we've looked out into the universe and found phenomena that we cannot currently explain. And they've worked very hard at explaining it in various ways. So, for example, dark energy, the problem is basically that it's almost like there's a kind of, I guess you could explain it, if there's particles out there that have an anti-gravity element to them, kind of causes things to spread out more than you would expect otherwise. So they study galaxies and how fast galaxies spin and stuff like that, and they find that, I forget if they spin, I think they maybe spin slower than expected. You can contrast it with how much light is being emitted, and it's very complicated. But they look at how much light is being emitted from the galaxy to determine how much stuff there is, how much mass. And so that gives us how much gravity there is, and we can calculate how fast things should spin and that kind of stuff. And there's a discrepancy there. So, yeah, I'm not a super expert on that problem of dark energy, but it's kind of about the universe spreading out for some reason, I think. Okay, so we can have open problems. Our understanding of physics is not yet perfect. Okay. So yeah, physics is sort of the foundation of science and our understanding of everything. And math is used to explain all of proper physics. Now, QM is part of physics. I shouldn't really have this as a separate thing. Inside of physics is really our modern understanding of physics can be divided into two separate parts. Gravity, because we have trouble mixing gravity with our other everything else that we know in physics. And then there's everything else. What's everything else? I I'd like to just call it particle physics. There's several ways I could describe this, or several names that I could attach here. It's often called the standard model of particle physics, or just the standard model. Okay, so I could have said there's gravity and there's the standard model. I could say there's gravity and then there's particle physics. Or I could also say there's gravity and then there's quantum physics. Quantum physics. And this is just getting into terminology, but you could say there's gravity and there's quantum mechanics. That's okay. Normally, when we talk about quantum mechanics, we're kind of talking about, there's emphasis more on just talking about electrons, and sort of quantum mechanics is often talking about sort of the older version of quantum physics. We have a more modern version called QFT, which is called quantum field theory. This is the modern version. So the standard model makes use of quantum field theories. There's QED, I know I'm getting a little detailed, but QED is quantum electrodynamics. That describes electrons and photons and the electromagnetic force. And then there's QCD, it's quantum chromodynamics, I think I'm saying that right, which describes the strong force and quarks. And there's quantum flavodynamics, something like that. Flavor dynamics describes the weak force. So there's 4 forces in physics. There's gravity, and then there's electromagnetism, the strong nuclear force, and the weak nuclear force. And so these 3 are kinds of quantum field theories. So all different ways of describing quantum physics, okay? And that's just the physics of how our modern understanding of how particles interact. Okay. And there's a long explanation of sort of the history of this word, particles. We really think of them more as waves, but it's this complicated thing to talk about. What is it? What exactly is meant by particles? There's kind of, depending on the context, if you're talking about a classical context, meaning the old way of thinking before all this quantum stuff came into our understanding, the old school way of thinking is that the particle is like a bullet or a billiard ball, like a ball. That's the idea. But the modern version is we still use this word, basically. We could have maybe come up with a new word to describe it, because it's almost, it's not exactly a misnomer, but it's maybe a poorly chosen, it's perhaps poorly chosen that we still use this word, because the modern notion is that particles are basically waves. But in some ways they have characteristics of waves, and in some ways they have characteristics that is like balls flying around. So there's this thing called particle wave duality, which is getting too detailed. But this whole thing of, if you search this kind of stuff like particle wave duality, you'll find all kinds of weird, interesting stuff. So naively, if you're new to this kind of stuff, you could think, well, the stuff that we're all made of, there's really 2 types of particles. There's matter particles, so you can think of that as physical stuff. And then there's these things called bosons, which they're basically, how to describe it? They are force-carrying particles. So I want to talk more about this in the future, but I don't want to go too deep down into this right now. But this is an interesting thing to search about. So you might, if you're new to this, you might think to yourself, well, these these matter particles, for example, the electron and the quark. And this is what your body is made up of. You're made of electrons and quarks, basically, and in terms of matter. And so you could ask yourself, well, are these like billiard balls flying around, or are they more like waves? The answer is not, the correct answer is not that they're one or the other. The correct answer is more complicated. So, but naively, you might go into it with this question in mind: are these matter particles wave-like? Think of waves in the ocean, or think of sound waves. Okay, are they wave-like, or are they like little balls flying around? And that's a good motivation to get yourself thinking about this. Now, there's something called, so what really got me interested in physics in the beginning, there's this thing called the double slit experiment. So we have a wall, and then let's start by having just one hole in the wall. And from over here, we shoot electrons this way. We could use other particles, really any particle, but because I talked about matter particles. By the way, matter particles have a fancy name. They're called fermions, okay? I'll just write that for you, but I'm going to erase it if you want to know. Fermions. These are matter particles. For example, the electron, the quark. There's only one other, the neutrino. Okay, those are fermions, matter particles. But it also, so I use that as an example to get you thinking about it, because we tend to think of when you think of your body, you think of this as stuff, matter, right? Matter particles. Of course, there is also electricity inside of you, right? In your brain, there's electricity. So what is electricity? Well, those are, in part, it's photons. It's light moving around. So to have a complete description of what you're made of, you also need these bosons, which are the force-carrying particles. So all the elementary particles, all the fundamental particles, are either fermions or bosons, and bosons carry force. And so one way to think of it is, imagine both of us are on boats. You're on a boat, I'm on a boat, and I'm here, and we're just sitting still, but then I throw a ball to you. And the moment I throw the ball, I start pushing off this way, because that's one of Newton's laws. For every action, there is an equal and opposite reaction. So because there's momentum going in this direction of the ball, there has to be an equal and opposite reaction. So that means that I get pushed the other way, right? Hopefully that's intuitive. So I throw the ball to you, and I get pushed this way. So I start moving in this direction. And then when you catch the ball, there's this momentum coming this way towards you. You catch it, and then it starts pushing you this way. So we exchanged a ball, but we both start getting pushed away from each other. So that is sort of the picture you can have in mind, the analogy of the exchange of a photon between two electrons. Both of our boats are electrons. We exchange a photon, and we both get pushed in the opposite direction. And it doesn't matter if you throw the ball to me, the same thing happens. We both get pushed away from each other. If that doesn't make sense, run through the same argument again. You throw the ball, you get pushed back. I catch it, I get pushed this way. It doesn't matter who threw the ball in which direction, we both get pushed away. And so electrons, they repel each other. So it doesn't matter which direction the photon was exchanged, they're going to repel each other. And when we think classically, the old school way of thinking is that these two electrons, that there's this electric force that repels them from each other, and that, so this is an equal and opposite force. So we're kind of skipping we're no longer really analyzing about this photon being exchanged. We're just talking about how the electrons repel each other now. Now, there are photons being exchanged, but just to simplify things a bit, we're just kind of not thinking about that. So the old school way of thinking, the classical way of thinking, is that these electrons continuously repel each other. So let's go back all the way to here. So if this is an electron and this is an electron, and let's say they're both moving upwards with equal velocity, they will basically get repelled, and so they'll maybe not as steep as that, but maybe like this. There's a symmetrical image here of them getting repelled. Okay? And the classical idea is that this happens continuously. So at every moment there's equal, well, the force, there's this equal and opposite force, right? Now, because the force is equal and opposite, it conserves momentum. See, so momentum, what is momentum? Momentum we usually write as P. So this is the classical version. There's a quantum mechanical version of this as well. But P is the momentum. We choose the letter P for some reason. Equals mass times velocity. You don't need to worry about it too much right now. But basically, it has to do with the Newtonian idea that there's for every action, there's an equal and opposite reaction. So the forces sort of have to ultimately balance out. And so yeah, for every bit of force in this direction, there's an equal and opposite force in this direction. So the net force is 0. And that's another way of saying that the momentum is conserved. Okay, conservation of momentum is one of the most foundational principles in physics. It's extremely... My voice just cracked in a very silly way. It's extremely useful. Like, there's one time I got, when I started playing with a fidget spinner. Is that what it's called? Fidget spinner. For the first time, it was interesting because the fidget spinner is actually kind of cool. If, let's say you hold it so it's right in front of you, and, you know, obviously the fidget spinner is like this thing, kind of spirally shaped thing, right? But I hold it right in front of me and I spin it. Basically, I can move, so here are my hands, okay? I can move the fidget spinner around, I can translate it without changing its orientation, without rotating it in any way. I can move it around freely, but as soon as I start to rotate it, I spin it, right? So it's rotating along this axis going through here, right? As soon as if I could apply more spin to it, no problem, or I could apply a force slowing down the spin, and that behaves as you would expect. But as soon as I start like rotating it in a different way, along a different axis, so I just take it with my hand and I like turn it this way or something, over in this direction, like around this way, you know? Any other rotation along a different axis, what happens is I feel it push against me. And this is sort of an odd sensation, right? If you're carrying a box and you can't see inside the box, and then we're used to like, okay, I feel the box is, I feel the weight of the box. It has this much weight. I can move it around, I can translate it as you would normally expect. And then normally, if nothing is spinning inside of the box, which is the normal situation, you can just kind of rotate the box as you would expect. But if inside of this box, you can't see in, if there were a fidget spinner spinning, then certain rotations along this same axis of spin would behave as you would expect, no surprise. But when you start rotating, if you just try to turn the box in some arbitrary way, it will push against you. It's like the box is alive. What's going on? So it's actually surprising. And I think that's why fidget spinners were a popular toy for a while, because it actually gets you thinking. So what's happening is that there's angular momentum. When you spin the fidget spinner, there's angular momentum. Basically the idea is you're basically storing energy in the spin of the fidget spinner. If there were no friction with the air or anything, I mean, in theory, this could spin forever if it weren't losing energy to other stuff. The big way that it's losing energy is through contact with the air. There's other ways that it loses energy too, but yeah. So forget why I got into this about the fidget spinner. But this is then conservation of angular momentum. Okay. It's a similar idea, but I'm not going to get into all the angular momentum stuff. It's a little more complicated. If you study about it, keep in mind there's two types of angular momentum. There's this intrinsic angular momentum, and then there's extrinsic. So if we're talking about the Earth, I'll just quickly talk about this. If the Earth is spinning around the sun, this orbit around the sun is the extrinsic angular momentum, and then the spin of the Earth itself along its axis is the intrinsic angular momentum, and these are separate. And that confused me in the beginning because I was like, which one are you talking about? And it usually wasn't specified. So keep those totally separate in your head. Extrinsic angular momentum and intrinsic angular momentum. And so there's conservation of angular momentum. It's more complicated. But yeah, conservation of momentum is extremely fundamental. It applies in I think all of physics. I don't think there's an example. I could be wrong. I don't think there's any example where it's violated. Whereas, for example, conservation of mass is violated when we talk about nuclear physics. Conservation of energy is pretty generally true, but it's actually violated when you talk about cosmic inflation, when you talk about, when you talk about dark energy. But when you talk about, so cosmic inflation is this idea that the universe expands, that space itself expands, that in the early moments after the Big Bang, in the early moments of the Big Bang, space was expanding very, very rapidly. And if you look, they say that the Earth is about the universe is about 13.8 billion years old, but the radius of the observable universe is about 45 billion light years. So starting from the center of the Big Bang, going outwards, light would have traveled 13.8 billion light years. However, the radius of the observable universe is 45 billion light years. So how is that possible? It's possible because because space itself expands. And it was expanding at a faster rate back in the past, closer to the Big Bang. But I believe that's an example of a violation of the conservation of energy. So, but I do not know of an example of a violation of the conservation of momentum. In any case, I'm pretty confident that all of the standard model of particle physics, all of our modern understanding of physics conserves momentum. I'm pretty sure about that. Yeah, I think so string theory is totally speculative. We have no idea if string theory is true or not. In fact, I tend to think it's not true. So that's why I haven't talked about string theory in here. So string theory is just a big question mark. And lately, people are not too happy with how it's going. So, put a cross through it for now. I'm a little skeptical of it, but it has made some good progress in mathematics of physics and certain things. So it's not totally in vain if it turns out to be wrong. Okay, so these particles repel each other, and they repel each other with a relatively simple law, at least in the classical picture, the old school picture, which is that there's an inverse square law. So an inverse square law is, what's a simpler example? Should I write out? I think it's called Coulomb's law. I don't know if I remember it exactly, but I think we have some charge 1. I'll label Q1, and we have some charge Q2 over the distance squared. And this is basically it, but we'll have some kind of constant. I'll put it over here on the side. It could be down here in the denominator or up here. I don't even really remember. But the important thing is that you have distance squared down here. That's why we say inverse square law, because inverse, in this case, we're talking about the reciprocal, and we're talking about the square. So inverse square law. And we see, at least classically, this pattern arises quite a lot. So, and I'll just say on this side is force. Okay. So, as far as equations go, this is not the most complicated equation in the world. I believe this is called Coulomb's law. It's sort of the electric force law. And sorry if I got some detail wrong. I mean, I don't think the K is right. There's something else here. But some constant. That's the point. And so you see lots of inverse square laws, particularly in classical physics. But you can see that as they move, the distance changes. So yeah, so Newton was looking at similar equation. Let's see if I can remember. This is like basic physics, but can I remember the equation for Newton's gravity here? So I'll say again force. Now we're talking about gravity. There's some constant G, big G. I don't like that. That looks like a 6 to me. Some constant big G will again have distance squared. So note that this is, when people talk about gravity in sort of a basic classical way, you might be talking about like the surface of the Earth, or you're somewhere on the surface of the Earth, and the downward acceleration is roughly 9.8 meters per second squared. Okay. Let's see, downward acceleration. I put a minus sign because it's downward. And so we can talk about that situation. So here you have I'm not going to explain all of calculus here. I'll just quickly go through this. That what this means is you have a negative 9.8 t. So this would be, this acceleration equation is constant. It's not dependent on time. And yeah, I'm going through a quick overview of this. But just using calculus, this is your given that the acceleration is constant. The gravity is constant. So that means we're not caring about our distance between objects and the Earth. Right? If we were talking about the moon, we need to consider the distance from the Earth. That will factor in. But to close approximation, we just consider this constant for our purposes. If we're talking about, say, an airplane, the difference in gravitational pull on the airplane when it's parked in a hangar versus when it's a few thousand feet above the Earth, it's not that different. So we just simplify things and say that the gravitational pull is constant. So we have a constant for the acceleration, a. Using calculus, we find that it's this plus an initial, we can say an initial velocity. Now, if you don't know calculus, don't worry. This is not going to make much sense to you. It's okay, because we're going to move on pretty quick. I just want to briefly touch this. Acceleration, velocity, and then we have position is going to be, we take the integral of this. So we got this velocity equation by taking the integral of this acceleration equation. And I could put of t here for both of these, but because they're functions of t, they're functions of time, but I'm not going to. We also need to think about units and stuff, but I'm kind of glossing over it. But this one, we take the integral and we'll get 9.8 over 2 t squared plus the initial velocity times t plus some initial position. So these are our equations of acceleration, velocity, and position with respect to time for this simple case of gravitation. However, when we're talking about different distances, like different positions in the solar system, or we're talking about the moon relative to the Earth and stuff like that, the distance between the objects matters. And so that's where this simpler version of gravity, we can't use that. We need Newton's law of universal gravitation. Newton's gravity. Now, this is the classical older picture. We have a more modern picture, which is Einstein's gravity. That's general relativity. General relativity, that's our modern understanding of gravity. It's different. But Newton's gravity is quite accurate. So if you're sending a probe to take pictures of one of Jupiter's moons, you actually don't even need Einstein's gravity. Newton's gravity is accurate enough. But if you want to study black holes, you really need to use general relativity, not Newton's gravity. Some people don't realize, but the concept of a black hole can be explored conceptually in Newton's gravity as well. And the concept of this kind of singularity actually dates back before the concept of a black hole related to general relativity and all that. It's a bit of an older concept. But anyway, so this will have it's basically the same pattern of this formula that we see up here. We have some mass 1 and a mass 2, I believe that's it, times some gravitational constant. Okay, so these are both inverse square laws. And what Newton wanted to do was to calculate orbits, to figure out, for example, predict the motions of the planets using this law. And it's not so straightforward. Newton invented calculus in order to make those calculations. And there's another person, Leibniz, who also invented calculus at about the same time. Okay, and so going back here, so this is the classical picture, and we have a more accurate understanding, which is quantum mechanics. So going all the way back to quantum mechanics, what am I doing here? Let's just go down here. The super interesting thing that gets a lot of people interested in physics is called the double slit experiment. I should learn how to make actual lines, but this is good enough for now. Whoa, that's not good. So we start with basically a wall, but there's a hole in it. So you could imagine let's also picture the sort of 3D version. We just have a barrier of some kind with a little hole in it. And we take a gun that shoots electrons, and we shoot electrons at the hole. It passes through to a wall behind it. And we look at how the electrons, the pattern that they make as they hit. They come in one at a time. Okay, so we have the 2D picture comes through, it hits this wall. Pop, pop, pop. Now it forms, in this example, this is one slit. It basically forms this sort of, I believe it's a Gaussian distribution. It's like the normal curve, I think. Could be wrong. Need to check that. But basically it congregates in this central area. Pretty consistent with the notion of balls being shot through this barrier with a hole. There's nothing surprising here. And yeah, the old school notion of a particle is sort of consistent with this. Now we do something new and we create two slits. Okay. Oh, there's a limit to how far it'll let me go back, huh? Let me just erase. Oh. Alright. Let's just go down here. Okay. So now we have the same thing. But two slits is going to change things. It doesn't need to be that far apart. Two slits, so the three-dimensional picture can have like a slit and a slit. And we have a gun shooting these electrons. They're one at a time. And they hit some wall behind here, and they form a pattern, just like we had. I shouldn't have erased it. We had a pattern of imagine like if you were shooting at a target, or let's say you had some kind of robot shooting at a target, and it has a certain amount of accuracy that is it's consistent in its randomness. So it congregates around a certain point. And it's rare that it hits outside here. Now, in the example with two slits, now we get a very surprising pattern. Okay. And the pattern, we see these bands. So we see bands. Pretend these are all dots. So there's areas with a lot of hits, and remember it's all coming in one at a time. And then there's areas with not so many hits. Now that's weird because classically what was expected was that we would have just now 2 possible areas with hits coming through these 2 slits. Or I guess they would be more like, because I'm talking about these sort of vertical slits, so might look, we would expect something like this. Not all these bands. Now I'll give you an actual, I'll find you an actual picture of this. There's a bunch of pictures. So here's an this is actually done with a laser. You can actually do this with a laser pointer. Okay. These are other examples using, now it's light. Again, it doesn't matter what kind of particle you're using. If it's a laser pointer, those are photons instead of electrons. Let's see if we can get something with the electrons. Basically, this is the pattern overall. It's called an interference pattern. Looking for something with electrons. Interference pattern with electrons. Yeah, something like this. This is probably actual experimental data. This is what we're getting. These kinds of bands. So this is surprising. It's, well, not anymore after. But in the early 1900s, this was surprising. So again, the double slit experiment. Double slit experiment. Maybe I'll put a video in the description that further illustrates how weird this is. Basically, it gets weirder because they set up a device to measure, to observe which hole, which slit the electron went through. So now we start measuring it. And when we measure it, it switches back to this pattern. So when we're not measuring, it's this pattern. Now, there is a somewhat tempting way to sort of simplify this whole mystery. And in fact, Neil deGrasse Tyson explained this. However, for reasons I'll get into, it's I want to say it's wrong. It's not that it's necessarily wrong, but it's not describing all of the mysterious stuff that's going on. It's not complete. So the description goes like this. It's that when we start to measure which slit the electron passed through, we're interfering with the experiment, of course, and basically it's like this. So this is actually how Neil deGrasse Tyson explained it. Have you ever had coins stuck in the crack of your sofa or stuck in the crack of a car seat or something? And then you reach down, you can't see, but you reach down to grab the coins, and the act of reaching down pushes the coins down further and makes it even harder to get at. So your effort to find exactly where the coin is has disturbed the position of the coin. So this is an extremely common, ubiquitous thing in quantum mechanics, that the act of measurement or the act of observation will have an effect on the system. It will have an effect on the thing that we are trying to measure or observe in all of quantum mechanics. That's how nature really works. And it basically makes sense because in order to... So let's imagine the electron as a little ball. We actually have to bombard it with photons, maybe, to try to find its position. And bombarding it with photons will cause it to, will have an effect on it. It will change its position function, to use technically correct language. And so, yeah, so in our classical world, kind of like now there are not two separate worlds. That's a common misunderstanding. The world is quantum mechanical. They're not two separate worlds. It's not like little things act quantum mechanically, and then but when you have a lot of things, a lot of little things, like you have millions of particles, now they start acting classically. In a way, they act classically just in that the classical physics is a useful approximation of what happens in most cases. However, it breaks down in the extreme cases. And we know that the quantum mechanical story is the correct, or at least more accurate story. Now there may be an even more correct story. So I didn't talk about it yet, but we don't know how to bring gravity and particle physics together into one framework. This is really the biggest problem humans are faced with right now, in at least from my point of view. At least in physics, this is this giant glaring problem. There are some physicists who say that this is not a problem. I very, very strongly disagree with them. I think it's a huge problem. And it's something that, Einstein in the second half of his life was focused on this problem, bringing basically quantum physics and gravity together. This is the giant open problem. And I find it extremely interesting, extremely fascinating. So getting back to this, what was I talking about? So in the classical world, which is incorrect, okay? There's not two separate worlds, and both of them, there's not the world of quantum physics and then the classical world, and they're both valid in certain circumstances. No, the world of classical physics is wrong. That house of cards has crumbled. It's wrong. We still use it all the time, and if you're passionate about physics, you absolutely need to learn classical physics for multiple reasons. One, just in order to, let's say your approach is, I don't want to learn classical physics because we know it's inaccurate. I want to learn just quantum physics and gravity, Einstein's gravity. In order to even understand what the physics professors are saying, you need to know classical physics. There are also some principles from classical physics that still apply. For example, conservation of momentum. What's another one? There's these kind of complicated things called Lagrangians, which are extremely important. That's also carried on from classical physics. That's like, if you're a physics major at MIT, I think that's like third year or something, so I shouldn't really talk about it yet. But yeah, there's some things that do carry forward that are still applicable. Also, it's very hard to make any sense of quantum mechanics and gravity if you don't have classical physics as sort of a bridge between you and all this more complicated stuff. And you're also not going to understand what people are saying at all. So you really do need to learn classical physics if you really care about learning physics. Okay. But anyway, so to some degree of approximation, our ordinary world that we experience is sort of described, again, up to approximation by classical physics. And in that domain, we find our general experiences, well, we can keep making more and more precise instruments for measuring things. And you can always make something smaller and more precise. But that's not technically correct. There's a limit. And so it kind of reminds me of the effort to make smaller and smaller processors. So computer processors are built out of different things, but one of the most important things that they're built with is transistors. But you can only, you can't build a transistor out of one atom. You need, I think some of the smallest transistors are like 18 atoms thick, or I think it's smaller now actually. It might be like 14 atoms thick, which is like ridiculously small. But you can't, there's a limit. I mean, even like 6 atoms across, I think is just not possible. And so this is related to is it Morse's law? No, it's Moore's law, I think it's called. About how small we can make computer processors and all that. Anyway, with doing experiments, you run into limitations at some point. Your measuring apparatus has to be, I guess in the limit, your measuring apparatus in a sense could be a single photon. That would be the limit. It can't get smaller than that. There's no half a photon, there's no half an electron. That's the limit. So in the true world that we've discovered in the last 120 years, we've kind of run into these limits, and we've found that you can't just keep making things smaller forever. There's a limit. It's kind of like when you think of, if you take an object, take a piece of wood, cut it in half, then cut it in half again, and then again, and then again and again. This is an old riddle. Like, there's a question: can you just keep cutting it in half forever? The answer is no. Eventually, you're left with one atom, one single atom. You could break that into electrons and quarks, and then so you have a collection of electrons. Eventually, you get down to one electron, and you cannot break that down any further. Okay. So we have these limitations, and so when we're talking about one electron, it's pretty sensitive when we start shooting photons at it, which photons are light. So if you want to take a picture of something, you need light. So you have to have photons coming at it and interacting with it in some way, generally maybe bouncing off of it, in order to create some kind of image. So yeah, so when we get down to the sort of technical details of what stuff is made of, we run into this kind of interesting new world of limitations, and things work differently than what we're used to, and this is the world of quantum physics. So there's this somewhat simple, and I would dare say naive, viewpoint that all of this can be explained simply with this logic of the fact that when we try to measure something, we interfere with the thing itself. And this is Neil deGrasse Tyson's sort of, unfortunately, simplistic and ultimately incorrect view of quantum mechanics. He just brushes it off and says, it's all explained by this. Just like when you reach into the seat to try to grab change, you accidentally push the change down further. It's like that. And so when we try to measure which slit the electron goes through, we interfere with it, and in the lingo of quantum mechanics, we collapse the wave function and force it to be in one of these two states of going through this slit or the other one. But before that, if we don't measure this, okay, can I erase this? It's a painstakingly slow process to erase this. But before this, what's actually happening is the electron is more like a wave. So that was a major discovery. It's actually more like a wave. But this wave can look maybe more like this, have more like a direction about it, in a sense. And so this electron shooting through is not like a ball shooting through. It's more like this concentrated wave shooting through. But our gun works more like, okay, we have this electron gun, it's called actually, is shooting through sort of like this concentrated wave. It's not like if you drop a pebble in a lake and it's going out equally in all directions. It's sort of got this, it actually has momentum. It has, so that's the quantum mechanical version of momentum. It works differently than this. It's a little more complicated. Everything in quantum mechanics is conceptually more complicated, but actually the math is, you could argue, is simpler. Many people learning it will not feel that way. But so we have this wave coming through, and so what happens is that the waves come through and then they it emanates outward. So in the simpler case, the waves come through, and then, and you, by the way, you can do this with normal waves, like in a classical world. It just sort of emanates out like this. Okay, and in the double slit case, they emanate out and they interfere with each other. So there'll be certain areas where there's what's the word? It's destructive. The wave interference will be constructive in some areas where you have these bands that are, that's where the electron is usually found to hit the measuring plate here that we've put on the other side behind the slits. So there's areas where the wave interference is constructive, and there's areas where it is destructive. And so let me bring up this. Oops. What is that? Oh my goodness. There's a whole parallel world over there. Okay, so this, the probability still needs to add up to 1. So if the electron makes it through the slit, which maybe is not always the case, or sorry, if it goes through this first partition, sometimes I'm sure it just hits the partition and doesn't go through. But if it went through, it will collide with this screen back here with, let's say, 100% chance, or maybe it's close to it. Maybe there's some chance that it goes flying off towards the outside here. So, but close to 100% chance that it collides with this screen. And so even though the interference pattern will be more complicated, we basically say it needs to add up to 1. This is a probability distribution. So this is the thing here. It's this is when we observe which slit it goes through. We get this pattern, and which is more in line with our classical expectations. But when we don't measure what slit it goes through, basically there's this wave that goes through both slits and interferes with itself and forms this interference pattern. And by the way, this interference pattern, you can also find, I kind of explained this already, but you can find the same interference pattern in classical physics. You can have waves that interfere with each other. You could be talking about waves in a body of water. You could be talking about waves, sound waves. You could be talking about, I believe classically you could be talking about waves of light. In other words, electromagnetic waves. You could be talking about polarity of light and that kind of stuff. And you still classically can get interference patterns with any kinds of waves. But what's weird here is the fact that when we try to measure which slit it went through, the pattern changes. That's the strange thing. Okay. And so the Neil deGrasse Tyson version, the simplified explanation is It's just a consequence of the fact that now we're talking about these little objects that are very sensitive, and when the act of measurement itself changes the thing. That's the full explanation, is what Neil deGrasse Tyson would say. That sounds nice, and it is extremely true that the act of measurement changes the state of things, of anything in quantum mechanics. All the things in quantum mechanics are described as what we call quantum wave functions. Okay. And you can have quantum wave function, physicists will actually, it sounds weird, but they'll talk about the quantum wave function of the universe. They'll talk about somewhat, perhaps in a hand wavy manner, but they'll talk about the quantum wave function perhaps of the experimenter, the quantum wave function of the measuring apparatus. Those are sort of loose terms, I guess, but there's nothing wrong with that kind of language. But if we're talking about an electron, we'll talk about the function of the electron, you could say, but the more verbose version, as we say, the quantum wave function of the electron. And quantum wave functions, we often denote, for whatever reason, the Greek letter psi is often used. I believe that's a capital psi. Some people will say psi, but I find that difficult to pronounce, so I'm a little lazy, so I just say psi. So you might have psi as a function of time, for example. Or you could have psi as a function of position and time. This is a quantum wave function. So you can write it like this. There's another kind of notation you might see where people write it like this. This is called, sometimes you could call it Braket notation or Dirac notation. Anyway, just another way of writing things. So, everything in quantum physics is a wave function. Okay. All right, but so I'm not going to go into extreme detail, but it's my opinion, very, very strong opinion, that this simple explanation that I gave you, that this whole story is explained by simply saying that the act of measurement affects the system itself. This is not enough to explain quantum mechanics. And again, I won't go into detail, but I will tell you, if you want to dig deep into all this stuff, there's this thing called Bell's inequality. And this was the person who came up with this, his name was Bell, shocker. I believe he came up with this in the 70s, I think, 60s or 70s, and experiments were done, and they verified Bell's inequality with greater and greater certainty. And we're very, very certain that Bell's inequality is true. And Bell's inequality is a test for these things called hidden values or hidden value theorems. So again, sorry, this is very much an overview, but we have to start somewhere. So hidden value theorems, this is what Einstein wanted in quantum mechanics. So Einstein and many others found quantum mechanics disturbing, even though Einstein helped to develop quantum mechanics. There's a great famous debate between Einstein and a physicist named Bohr. And it wasn't just Einstein. There were it was EPR, I think. Einstein, Rosen, and Podolsky. Anyway, there were some others. And they were arguing for these basically a hidden value theory. I don't know if Einstein called it that at the time, but it was later called that, at least. So there was this debate over whether these sort of hidden values, so the idea is that, for example, the electron would carry along with it this hidden value, and when you measure, for example, the spin, which is the angular momentum of the electron, that then you would measure this hidden value, or something along those lines. There were these hidden values. And then Bohr disagreed and said, no, we need to take quantum mechanics basically at face value, and when you introduce this hidden value theory, you're kind of introducing stuff that we don't have evidence for, that's not needed. But Einstein, I think, would have argued, well, but this makes things sort of logically more consistent and helps him sleep better at night, and sort of resolves some of the more, I guess, disturbing or very confusing things about quantum mechanics. There's more confusing things than just this. This is the double slit experiment is sort of the tip of the iceberg. I don't find it disturbing at all, personally. Not anymore. I mean, maybe 10 years ago, I thought a lot about this. This is what got me really interested in physics. But there's different interpretations of quantum mechanics. And so at that time, maybe 10 years ago, I thought a lot about this, and then I came to my own conclusion about what I think about the various interpretations of quantum mechanics and where I stand on the whole thing. And my opinion hasn't changed too much in 10 years. But anyway, so there was this great debate, and Einstein was on the side of the hidden value theories, and then after Einstein passed away in the 60s or 70s, this guy Bell came up with the Bell's inequality, which gave us a way to test for hidden value theories or hidden values. And we tested it, and we found that that's wrong, that there's basically no hidden values, and so Einstein was wrong. And yeah, so if you want to get into the strangeness of quantum mechanics, I recommend learning about Bell's inequality. That's getting deep into the strangeness of quantum mechanics. There's also something called the delayed quantum eraser experiment. This is also getting very much into the heart of the strangeness of quantum mechanics. Yeah, those two things I would recommend if you're interested. And of course the double slit experiment, which I've talked about a bit here. Those three things in particular. There's probably more things. There's like weird, wonky experiments they can do in quantum mechanics where like they send the angular momentum of a particle through one path, and they send the what else would there be, like the position or the phase maybe of the particle in a different path. Weird things that they can do. There's also something called quantum tunneling, which I don't find weird at all when you think of this wave nature of the particles. I don't find quantum tunneling strange personally, but maybe I'm missing something. Yeah, I guess I'll leave it at that for now. I haven't even gotten into anything about game development, programming, or what was the other thing? Well, there's some math here. Yeah, talked about math and physics. I'll very briefly, because I want to end this video, say there's this thing called a quaternion. Oh, you know, if you've done some game development, you might have heard about it. I'm not going to explain why or how, but the quaternion is very much related to. I'll say it's very much related to the electron and the spin of the electron, or what can more, in more words, you could call it the angular momentum of the electron. And not only the electron, but all of the matter particles, all of the fermions. They all have what's called half spin. They're all what are called half spin particles. So we say that their quantum spin is 1/2 fermions. There's an M in there. These are the matter particles. So the fundamental matter particles all have spin 1/2. Now it's very confusing language, unfortunately, for historical reasons, and actually, yeah, I don't have time to get into it anymore. But quaternions can be used to describe the 1/2 spin, the angular momentum of these particles. You don't have to use quaternions, but basically, I'll try to say it in kind of technically correct language. I think that the quaternion algebra, I'll say that the unit quaternion algebra is isomorphic to the spin 3 algebra. So that's a bit of jargon. It's fancy language for saying that basically the quaternion algebra, so this business of multiplying together quaternions, is in some way you can look at it and find that it's basically the same stuff going on there as what is happening with these half spin particles. So in other words, you could describe you can describe the angular momentum of all the matter particles that we know of using quaternions, using this quaternion algebra. You have the same structure there, mathematical structure. It's different versions of the same thing. So we can map from one of these mathematical structures to the other one, and vice versa. So we have this two-way map, which is basically a correspondence, or almost I want to say equivalence, but we say they're isomorphic, which means that we have this two-way map. They have the same structure. They're kind of the same. They're not exactly the same thing. How can I explain it? It's like in geometry, you have congruent triangles. You have two triangles in different places that are congruent. It means that they're the same size. They're basically the same triangle, they're just in two different places. So it's wrong to say they're the same triangle because they're two different triangles. But in terms of their characteristics, they're the same. It's the same structure. See what I mean? So because we can map between these two structures in sort of a complete way, we say that they're isomorphic. It just means that they're in some sense they're sort of equivalent. In some sense, I want to say that they're the same, but that's just kind of wrong. So you can almost think of them as the same. And so quaternions are used in game development. They're very powerful mathematical objects. They're also very tricky and confusing, and also the angular momentum of fermions is also tricky and confusing. But if you can understand quaternions, which is no simple task, there's still actually a lot. See, the language of quaternions is just different from the language of these half-spin particles. Physicists use all this language that takes a long time to get used to. So I wish I could tell you that if you understand quaternions, which is no easy task, but if you understand it, then you're going to easily understand half-spin particles and the angular momentum of all of the fermions. However, unfortunately, that's not true. That's really not true. It's not easy. If you really want to understand this stuff, it's not easy. Nobody said it was easy. However, I think it's interesting. Now, So that was a lot about physics. There will be videos here where I talk about physics. There will be videos where I focus on math. There will be videos where I focus on programming, and there will be videos where I focus on game development. So hope you enjoyed it. Let me know if you have any questions or ideas for me for content, because that helps me a lot actually. If you have, I need ideas. So thanks. Take it easy. Goodbye. Have a good one.